Hi there, and welcome to Chemistry 20. We're going to be starting on the first unit, which is the chemical bonding unit. So to start off, your booklet begins with terms that you should definitely know, and you'll be able to fill this in as we go throughout the unit there. So to get started on this unit, we're first going to go into some definitions. So first off, we need to know what a pure substance is. Now, a pure substance, it only contains one kind of matter, and it can't be separated into any smaller parts. Now, this one kind of matter can be either elements or compounds. Now, what is an element? An element contains only one type of substance that cannot be separated by chemical or physical means. So elements can be metal, non-metal, they can be transition elements, so on and so forth. So because this is a definition, we're going to want to highlight this. Okay. Now what I'm going to do here is quickly flip over to my periodic table, just so we can take a look at it. Now, each of these boxes here represents an element. So let's say this box here, hydrogen, that is one element. The element below hydrogen is lithium, sodium. These are all elements, okay? Now, when I say that elements can be metal, non-metal, or they could be transition elements, what that's referring to is the fact that periodic tables are organized very smartly here. So with the exception of hydrogen here, okay, everything to the left of this bold staircase line, so this staircase line I'm talking about here, that goes from boron, okay, down by aluminum and silicon, down by germanium and arsenic, antimony and tellurium, and down all the way beside polonium and astatine. Okay, so this staircase separates your metals, which are on the left-hand side of the staircase that I just referred to. The only exception being hydrogen. Hydrogen is listed over to the left here because it acts like other elements in this first column here. Okay, but hydrogen is a non-metal. Now, everything to the right-hand side of the staircase line, that is a non-metal. And what I should be doing is I should be also including group 18 there with our nonmetals. Another item or another feature of this periodic table that you'll want to be aware of is the elements that are right on the staircase line. They have properties of both metals as well as nonmetals. So these elements that are, in this case, they're going to be colored purple here. They are called our metalloids, or as this periodic table refers to them as semi-metals. And again, that just means that they have properties both of metals and nonmetals. We call them either metalloids or semi-metals. So some examples of elements. Okay, so I'm just going to list some elements that I just talked about. So hydrogen, let's say lithium, boron is an element, so on and so forth. Okay, now a compound, so that's another definition that we want to know. Okay. A compound is made up of two or more elements that are chemically combined. And with compounds, they can be separated by chemical means. So in other words, through a chemical reactions. Now, we have two types of compounds, either molecular compounds, which are formed by two or more nonmetals binding together or bonding together, or ionic compounds. So an ionic compound is formed when you have a metal bonded to a nonmetal. So for some examples of some compounds here would be sodium chloride or NaCl. So I'll write the chemical formula and then I'll write the name. So this would be an example of an ionic compound because sodium is a metal, so it's to the left of our staircase line right here. So sodium can be found right here, and then chloride is to the right of the staircase line, so it's part of our nonmetals. Another example here would be magnesium sulfide. And again, that's another ionic compound, just because magnesium is a metal, which can be found in the second column or group 2. And then sulfur, that is a nonmetal, so that's why that'd be an ionic compound. Now, let's list some molecular compounds here. Water. So hydrogen is a nonmetal, oxygen's a nonmetal. That's why it's molecular. Ammonia, which is NH3. And there's many other examples, but that's just what I'll say for now for our examples of compounds. Okay, now elements are made up of one atom of a particular element, and it's represented by a symbol on the periodic table. So as we've looked with these elements on our periodic table, notice that each element has their own symbol to represent whatever the element is. So lithium is represented by the symbol Li, beryllium is represented by the symbol Be, so on and so forth. Now, oftentimes with these symbols, you'll notice that the first letter of one element is going to be capitalized, but the second one, if there's two letters that make up the symbol, is always going to be lowercase if you're only talking about one element there. Okay, if you had both of the letters capitalized, so something like this, okay, this would mean carbon, and then O would mean oxygen. So just be careful about that. Capital C, capital O is very different from capital C, little o. This is actually cobalt. Okay, so if you wanted to find all of these symbols that I'm talking about here, carbon is there, oxygen is there, and then if we look down in the transition metals, so transition metals are in between group 3 and group 12. Okay, cobalt is going to be right there. So just watch out for those differences. Okay, so like we said, an element symbol can have a capital letter or one capital letter followed by a lowercase letter. For example, the symbol for carbon is capital C, the symbol for cobalt is CO. And keep in mind that O is a lowercase o. Okay, and so I'll write down in these notes what I wrote on the periodic table there, versus if we have capital C, capital O, that's carbon, this is oxygen. Okay, so very crucial difference that you need to be aware of when using capital letters as well as lowercase letters. So as you see in this booklet, there are small sections with practice problems, and what I'd recommend is that you give these practice problems a try. So you can refer to the lesson guides in your Google Classroom to see which practice problems are recommended. You're welcome to do all of the practice problems if you need the extra practice, but that's up to you. What is required will be described in the lesson guides. Okay. So moving on to compounds and molecules. So these are a couple more definitions that we need to be aware of moving forward in this course. So a molecule is two or more atoms that are joined together chemically, so through bonds. Now these atoms can either belong to the same element or different elements. So if you see me making notes, I strongly recommend that you write those same notes as well in your own booklet. So the atoms can belong to the same element or different elements. Now a compound is a molecule that contains two or more elements combined together. So that's the key distinguisher between molecules and compounds. So molecules are made up of atoms that either belong to the same element or different elements, and compounds are a molecule. Compounds are molecules that contain two or more elements, not necessarily just atoms, but two or more elements combined together. So with this distinction, we can say all compounds are molecules, because all compounds are made up of atoms, but not all molecules are compounds. And that's because not all molecules have two or more elements that are making them up. So some molecules are made up of two or more atoms of the same element combined together. For example, P4, that is the symbol or the formula for elemental phosphorus. Another example would be sulfur, or elemental sulfur is S8. So whenever sulfur is by itself, there's always 8 atoms of it grouped together. Or another example would be ozone, which is 3 atoms of oxygen grouped together when oxygen is by itself, or oxygen can also exist as O2. So just a heads up, O3 is specifically called ozone, O2 is called just oxygen gas. So one can determine how many atoms are in a molecule by looking at the subscript, so that's the small numbers that follow an element's symbol. So if we take a look at H2O, okay, so this first symbol here, H, that's the symbol for hydrogen. Now if you don't have that memorized, that's fine. You can always look at your periodic table, find the symbol, and get the name from your periodic table. Okay. Now for hydrogen, notice that a small subscript 2 follows it. So that means that there are 2 hydrogen atoms in this compound. Now moving on to the next symbol, O, That's the symbol for the element oxygen. Now we don't see a small subscript number after the oxygen, and that means that there's only going to be one atom of oxygen. And last but not least, when we're reading a chemical formula, we should be denoting the state, especially if we are writing a chemical formula for a chemical reaction. Okay, so this symbol right here, that's an L, which means that this is going to be in the liquid state. Now, while we're talking about states, I just want to cover what all the states are that we will be going over in this course. So for our states of matter, here are our options. So L, obviously, that means liquid. AQ means aqueous. That just means that your substance is dissolved in water. S means solid. And G means gas. So those are all the states of matter that we're going to be covering in Chemistry 20. Now, let's move on to some examples where we're counting up how many atoms of each element there are in a chemical formula. So if we have CO2, looking at this chemical formula, I notice behind the elemental symbol for carbon, the capital C, there's no number. So that means we have one atom of carbon, and there's a subscript 2 after the symbol for oxygen. So I have 2 atoms of oxygen. Okay, now off to the side here, it says total number of atoms. Well, 1 plus 2 is 3. So there's 3 total atoms. For our next chemical formula, we have Ca and then in brackets OH2. So for Ca, or calcium, again, you can look up what the name is for an element. If you're just given the symbol, you can look it up on the periodic table here. So for calcium, I find it right here. So this is how I know the name of that element from the symbol. Okay, so again, I notice there's not a subscript number behind it, so that means there's 1 atom of calcium. However, for oxygen and hydrogen here, okay, both of those are in brackets. And what that means is that this subscript 2 that comes after those brackets, it applies to both of them, both the oxygen and the hydrogen. So I'd say, okay, there's 2 atoms of oxygen and there's 2 atoms of hydrogen. So in total, there's 5 atoms. Okay, so moving on here, there's more practice questions. Please refer to the lesson guide to see what is assigned. And I'm just going to move to the bottom here. Okay, so recall that the subscript, which is the small number after an element, tells you how many atoms of each element there are. So you need to know what subscripts are. You also need to know what coefficients are. So a coefficient, that's going to be a large number in front of the entire chemical formula for a compound. and it tells us how many molecules there are of whatever compound you're talking about. So, for example, we have 2 HCl. So, if we're looking here, okay, and we just temporarily ignore this 2, okay, we have 1 hydrogen and 1 chlorine atom, okay? But since we want to know how many atoms in total are represented, this 2, it's going to apply to everything that comes after it. So coefficients don't need brackets in order to apply to everything that comes after it. Okay, that's just assumed. So in total, we have 2 hydrogen atoms and 2 chloride atoms. So 2 plus 2, that's 4. Now, how many molecules of HCl do we have? Well, we have 2. So how many molecules is correlated with that coefficient? So the number, the big number that comes in front of the compound. Okay. Now with this next one, we have 7 H2O2, so that's 7 hydrogen peroxide. So how many atoms in total are represented? So you can kind of think of this as 7 times 2 with the hydrogens. So 7 times 2, that's 14. And then with the oxygens, that's once again 7 times 2. So I'm taking the coefficient and I'm multiplying it by the subscript number. Okay, so in total, we have 14 atoms of hydrogen plus 14 atoms of oxygen. That's going to give us 28 atoms in total. Now, how many molecules is in this 7 H2O2? Well, it's going to be 7. Again, you're just taking that number from the coefficient in front of the chemical formula. Once again, there's another practice section. Please refer to the lesson guide to see which questions are assigned to help you practice the concepts that we just went over.